you feel like if my voice has started breaking or my screen is lagging, let me know immediately so I can change my network. Okay. The today's fundamentals, like you're crystal clear with those concepts. And in the next class, we're going to look into advanced stuff, really advanced stuff. So, but my point is around 70% of the problems that you're going to encounter in greedy algorithms will revolve around today's class, not the second class. Okay. So, okay, like proving and everything will come in next class, because today I'm just going to give you a general idea and we're going to solve problems. Because if I would have included proving also in this class, then it would have been just a big monologue, right? Because I'm giving you definitions also and then I'm giving you proving also. So it would be a class like I'm just teaching you, and there is no discussions, there's no problem solving. So that's why proving and advanced stuff will everything will be covered in the next class. Today we'll have a basic foundation for greedy. Is it okay with everyone? Okay, so let's start. So basically, what are greedy algorithms? See, greedy algorithms are a class of algorithms that make locally optimal choices at each and every step with the aim of finding the global optimal. So these algorithms are simple, efficient, and often used for optimization problems where we seek the optimal solution from a set of possibilities. So now what does this mean? Anyone? Just unmute yourself and let me know what do you like, according to you, what is greedy algorithms?
Given a limited amount of choices, you choose the best possible option given, and such that it gives you the optimal answer.
Okay, so in a way it's correct, but do we always like suppose we have a choice, so do we always include that choice? When do we include that choice? So see, greedy algorithms basically, I'm going to show you the workflow also, how greedy algorithms, what is the exact way greedy algorithms work. But first, what is greedy? See, you have you let me start writing greedy also. Algorithms work, but first, what is greedy? See, you let me, okay, I think the screen share has stopped, right?
Yes.
Yes.
Yeah, right.
So see, you have some kind of problem including arrays, and so you want to find something like maybe maximum, maybe minimum. Let's not get into that part, but you want to find an optimal. Instead of optimal, I'd say the best possible possibility out of some n possibilities. So each step, let's say I'm at right now at this position, and mark my words, greedy algorithms are not only for this linear iteration. Okay, don't get the idea that in greedy algorithms we are going to iterate in this direction or this direction. No, greedy algorithms are not about that. So it's only about that during an iteration or during a step, maybe we are at this step, we'll try to include this in our answer, or maybe we'll try to take this as a choice, but we won't include it each and every time. We have a check. Okay, we have a check, and if it like satisfies this check, we'll say that this will also be included to our optimal solution. Now, how is this different? Like, why won't this always work? Anyone? Like, anyone? Why would, like, what is the case when this won't work?
When we have
There will
to
be uniformity then.
when we have to choose answer globally.
Yes. So this is like putting everything in like one statement. But yeah, the idea is correct. See, at this step, I'm deciding whether to include this in my optimal answer or not. Afterwards, I'm not going to come back, right? So at this point, the fate of this element is decided. So coming back to the set. So first of all, is this clear? I'm not going to like, I'm not discussing that thing that is going to come in the limitation part, but have an idea that greedy algorithms fail sometimes. And we are going to cover that also. When should we use greedy? So first of all, the general idea of like the upper level bird eye view is of greedy idea is clear to everyone, right? And let me know in the chat if you feel like my pace is slow, fast, anything. Let me know in the start only, so we can like so that I can Okay, it's slow. So I'm going to quickly go through the next slide. So what are the characteristics of greedy algorithms? See, first of all, greedy algorithms make decision on the current best option without considering the overall future consequences. Like I said, once you are done with the current element, you have decided its fate. Then they are greedy in the sense that they always choose the option that appears to be the best at the moment. So this is important, that it is the best option at the moment. You're not worried about, okay, maybe in future you might, like right now you decided that you're not going to take that element, and in future you cannot make a choice, okay, you will take back that element again. So this is not possible in greedy algorithms. Now, greedy algorithms do not always guarantee the global optimal solution, but they often produce acceptable results quickly. So we're going to come to this part. Like this will be much more clear to you. What do we mean by this when we cover DP also? So basically, let me give you a faint idea. You would have generally seen that the time complexity for dynamic programming problems is generally on the it's on more. It is more than the algorithm, like the time complexity for greedy, right? So I'm not going to go into that part, but the basic idea is because dynamic programming is in a way taking all the possibilities into consideration, and greedy is only taking that possibility that seems to be best at that moment. So that's why greedy algorithms produce acceptable results quickly. So what is the workflow of these greedy algorithms? See, first of all, we come with initialization. So initialization is basically you start with an empty solution or a solution with initial state. Then you select. So choosing the best available option on a specific criteria. Then there is a feasibility check. That is, verify if the chosen option satisfies all constraints and requirements. So this is very important. You don't always add elements to your like greedy solution. You have a feasibility check, and then you update. So update is basically modifying the solution and update the problem state. So update is if the solution that you're like, if the value that you're looking for is now, like the value that you have with you right now is more than that you had previously, so you're going to update it. Then termination. So termination is basically you will keep going to repeat the steps from 2 to 4 again and again until a certain criteria is met. Now, what is a certain criteria? A certain criteria can be something like you have to find at least something like at least so many values, or maybe you have to find the maximum or the minimum. So all of these are a condition. So while this condition is not met, you're going to keep iterating through 2 to 4. Come into the questions like after I'm done with the slide. I'm not going to like answer questions in between. So first of all, let me know, is anyone having any like difficulty in understanding what is the basic workflow? This is really important. Like this might seem not that relevant at this scale, but basic workflow that is followed even for harder problems. This needs to be followed. You cannot skip this feasibility check. If you're thinking, okay, I have solved problems in greedy algorithms that don't have the feasibility check, you are wrong. There is a feasibility check always. You might not be, okay, that is the feasibility check, but there is always this check. And if you're not having, if you cannot identify the feasibility check, or if you're 100% sure that your algorithm is missing the feasibility check, then your algorithm might not work like it should. So yes, is there any?
Yeah.
But yeah, this is making vague sense. What that actually means is I'm not getting.
Like just write your doubt in the chat. Okay.
Okay.
Okay, feasibility. Like okay, I'll discuss examples during the next slide, and I'll tell you what are these all the 5 parts in that. Okay. Okay, is it okay? Like next, we are going to discuss a problem, and in that problem, I'll show you all of these 5 parts. Now there are questions. Can't find when to use. Yes, this is the biggest problem. You cannot tell when to use a greedy and when to use a DP solution. So I'll come to this also. This is really important. So feasibility, I'll come to feasibility. Okay, DP is like a brute force approach. No. Okay, let me give you an example. If you have to find, maybe you're given some coins, and from those coins, each coin has a weight and a value, and you have to find uh, up till this weight, what is the maximum value that you can get. So this is a DP problem. If you apply brute force, let's suppose you have n coins, 2 to the power n. This is the complexity that you get. Okay, let me write this. Like brute force is different. Like there are all these three things are different. DP is different than brute force, and this is different than greedy. See, assume that you're given n coins and each coin has some value and a weight. Then you are asked that you have a bag that can withstand a weight, let's say WT. So what is the maximum value that you can get? So if there are n coins, you see total number of possibilities of choosing the coins is 2 to the power n. Like for each coin, whether you'll select it or not select it. So this is basically a brute force solution. A DP solution will be something like value into weight. So this is different, right? This is not brute force, but this is taking care of all the possibilities. And in this case, greedy is not applicable. I'll tell you why. This is one of those problems that you'll have to decide when to use greedy and when to use DP. Okay, coming back here. Okay, so is my voice breaking for or cracking for everyone, or is it for some people only? Okay, it's not breaking, right? Okay, fine. So now let me come to this problem. When do we use DP and when do we use greedy? So right now, you guys haven't been taught DP, but still I'll give you a fairly good idea. See, usually like if it is a single dimensional DP, then most probably like if the solution, like sometimes you can implement DP in O of n also. Then like probably you won't have to use that much of your brain to write the solution. But sometimes when you're not obvious that whether you'll use DP or greedy, you should look at the constraints. If the constraints are allowing in O of n square, then I'm pretty confident that the greedy solution won't work. Like if the constraints are asking you O of n, then you'll have to look at the language. What is it? And you'll have to look at the state. Like whether at each point, whether at each state, you can be 100% sure for each value whether to include it or not. Whether you are like whether at that state only. But if you are given constraints like in this problem, value into weight will be in order of, like if you multiply these two, this will be in order of 10 to the power 6. So by looking at these constraints, you should be 100% sure that a greedy solution won't work in this. Why? Because greedy is generally O of n or O of n log n. So this is one of the ways to look whether you're going to use DP or greedy. I'm not going to cover DP much right now because it hasn't been taught, but now there's also one case when n is in order of, let's say, 10 to the power 6, and still instead of greedy you'll have to use DP. So this will be much more clear once DP is covered. But usually around
Can
70.
you explain again? Can you explain again this point? When to use greedy and when to use DP? When you were saying like when we are using this, when we are using that.
Okay, yes, sure. So first of all, you look at the constraints. So let's say you have n and m. So if the total number of states for the problem, like you have to find some optimal result, and this optimal result depends on two things, maybe x and y. And this x and y, if you multiply these two, this is coming in order of nearly 10 to the power 6 or less. So then DP, I'm 100% sure that you'll have to use DP, not greedy. But it's also possible that you have only one state as x, like the optimal result is only depending on one state x, and x is in order of 10 to the power 6. Then it really depends on the problem statement whether you'll use greedy or DP. Now I'm not going to differentiate right now this case. Why? Because we haven't really covered DP. But if you want, I can give you an idea quickly.
Yeah, please give an idea. Please give.
Okay. Because you people might have solved problems earlier, right? This is not the first time that you're covering greedy. So basically, let's say we have an array. And from this place, like each one is having a value x, maybe 1, 2, like these are the indices. So this is a of 1, this is a of 2, this is a of 3, and all the way till a of n. So if you're asked, there are two problems now. The first problem is, what is the minimum number of jumps that are required to jump from this place to this place? So how will you solve this? This is basically a like A1 of 2 simply means that you can jump maximum length of 2 cells right now from this cell. So each one is having a value, and if you look at a current state, what is anyone saying something? So if you're looking at an initial state, you cannot directly tell what is, like, if this is going to be included or not. Why you cannot tell? Can someone tell me? Like, why can you not directly tell me in the final, like finally maybe this is the most optimal way to jump from this point to this point? Why can you not directly tell me at this point whether you'll come to this cell or not? Anyone?
Because if the arrow you are pointing to is further giving us 2 jumps, but if we go to the second arrow and we find it's giving us less jump, we don't know, because we have already made our mind that this arrow is going to give us the best result.
Yes. That's 100% true. See, I'm jumping to this point and I'm saying that I'm going to include this always, but it's also possible that from this point I'll first come to this point, and this is having a value 1, 2, 3, 3. So I can jump from here to here, but this is having a value of 1, 2, 3, 4, 5, 6, 7, 7. So from this point I can directly jump to the last state. So that's why this is a DP problem, and this is an O of n problem. I'm not going to cover this right now because this is like completely another topic. But in these cases, DP works in O of n. But usually around 70% of the cases, you'll find that looking at the constraints, you can tell whether to use a DP solution or a greedy solution. I'm going to cover greedy much more in detail today, so you'll get also a better idea like when to use greedy. And this thing, like this basic confusion between when to use DP and greedy, it will be clear only when DP will be covered.
Sorry, but I still can't get your point, because you said something like when there are constraints
Yes.
less than or equal to 10 raised to power 6.
Yes, the two things, like your optimal answer depends on 2 states. And
Okay.
if you multiply those 2 states, the product is in order of 10 to the power 6, like all the states. So in that case, don't think about solving this problem in, let's say this is n and this is m. N is in order of 10 to the power 3 and m is also in 10 to the power 3. So don't think about solving this in O of n. Just this is greedy. Like you are thinking in terms of greedy, and you are trying to get a solution which is O of n or O of n log n. That won't work. You
Okay,
get my
so
point?
if
So
there,
shouldn't it be
yeah,
10 ki power 8?
If like 10 to the power 8 also, DP also works in 10 to the power 8 sometimes. It depends
so
on, yes.
yes, I am saying, like, if it's a single array and
Yes,
it's O of it's n, basically the size of array is
yes,
going to be till 10 raised to power 6.
yes.
It's going to be O of n. Then we can think of greedy only after seeing the statement.
Like it depends on the problem statement, but yeah, like this problem, you won't be able to solve it using greedy. You'll have to use DP. And in these, like 70% of the problems that we cover in DP have more than one state around. है ना? So if you have more than one state and you are trying to use greedy when you are only looking at one state, like when you're using greedy, you'll be using only one state, right? So don't try to work with only one state. That's my point. If the constraints for one state are in order of 10 to the power 3, otherwise why will someone give you this constraint, right? Do you get my point? If the constraints for n is in 10 to the power 3, why would someone give you this much constraints if it could have been solved in O of n? So this is my point.
Yeah, getting your point.
So someone has already given you this coin change problem link in the chat. You can look at it, but basically it's that problem only which I just explained you.
Yeah, I have done that problem previously.
Okay. But yeah, the basic thing is majority of people don't get an idea when to use a DP and when to use greedy, and this really causes wastage of time. Like first you try to solve a problem using greedy, then you get a wrong answer, and then you shift to DP. Otherwise, you are trying to do it DP, you waste a lot of time, and finally you get a TLE. Right? This happens. Now, let's go back to the slides. So we'll look at this workflow using this problem. So this is one of these.
Hello.
Yes.
Ankit, previously you have said that if constraints x cross y is 1e8,
Yes.
then we can apply DP. But
Sometimes it depends on, like sometimes Codeforce's solutions do accept 1e8's operations. Sometimes they don't. So like you'll have to look the time. What is the time limit for that problem? If it's around 4 seconds, then it will be accepted. Otherwise, if it's 1 second, it won't get accepted. 10 to the power 8 operation. So it also depends on what is the time limit that you're given.
But the matter is that we are unable to construct a matrix of 2D matrix of 1
Yes,
yet.
like this will be covered in like DP only. Actually, you don't have to construct DP of size n cross m always. You can just construct a DP of size, like if my current I comma j state, I don't want to cover this right now. If this state is only depending on the last I minus 1, maybe let's say some j, maybe it can be anything, j minus 1, j minus 2, but this state is only depending on I minus 1. So then in that case, you'll only make a DP of this size.
Okay, okay.
The
We are
total
going.
operations will be 10 to the power 8 only. So these things happen. Like this will be taught to you in when DP is taught.
All right, we are going
This,
in the direction of tabulation and space
yes, yes,
optimization.
yes.
In
Like
this.
this, if you okay, you are aware of tabulation, right? I thought that you are not aware of it. So basically, this is the DP table that you draw, right? If let's say this, in order to find the values for this row, it only depends on this row. So there's no point in storing these values, right? So
Okay,
in
okay.
that case, you can just make a 2-row size. So first you'll try to get these values, then using these values, you'll get these values, then using these values, you again write like this is 0 index, 1 index, 0 index, 1 index. So you'll keep writing the next value using the previous one.
All right,
So let's,
Ankit. All
okay,
right,
let's
fine.
go back to the cadence
भैया ये
algorithm.
डिफरेंस वाला तो बिल्कुल समझ नहीं आया, बस वही आया कि ग्रेडी क्या होता है और कब यूज करते हैं.
Okay, so like at this point, it's really good if you are like if you have understood greedy, because DP is not covered right now, right? So I
हाँ
know
वही ग्रेडी, बस यही समझ आया क्या होता है और कब यूज करते हैं.
okay, like yes, this is more than enough. And like guys, do let me know if you are not able to understand something regarding greedy. Like it's much more important. Like it shouldn't happen that I'm answering random doubts regarding DP, and at the end of the day, some people are confused still about greedy. So this shouldn't happen. Okay, so let's go to cadence algorithm. So cadence algorithm is one of the fundamental problems regarding greedy problems, and this is one of the most often asked problems in OAs. Not only in OAs, you'll this like by OA I mean online assessments. Like cadence algorithms is also asked in interviews. This is like this was asked to me, cadence algorithm. So cadence algorithm, what is this problem? This is the largest sum. Like there are many variations of this. I was like actually to me not exact this problem was asked, a little bit variation of this was asked. But what is cadence algorithm? Cadence algorithm is you have to find the largest sum contiguous subarrays. So given an array ARR of size n, your task is to find the sum of contiguous subarray within ARR with largest sum. So first of all, let me know in the chat how many people right now are confident that they can solve this problem. Yes, no, anything. Okay, I'm seeing majority of yeses only. So I'll just quickly jump through this, okay? There's no point in wasting time. So basically, cadence algorithm is like, okay, you don't know how to relate it to greedy. Okay, now just write like if someone has doubts regarding like you don't know that this was a greedy problem or cadence algorithm, like the name of this is a cadence algorithm. So just quickly write that in the chat, or whether you are not able, like you're not completely sure that you'll be able to solve this problem if asked right now. Just those people, because I've seen many yeses right now. Yes, I'll relate. That's the basic point of this problem. I'll relate it to also. Just write a
Actually,
yes.
I've never heard about this. Actually.
Okay. But still, like I'll try to quickly wrap this because majority of the people have already, and it's easy only. Okay. So let's go back to, okay, I have got enough of responses. Underconfident in greedy. Okay, greedy is one of the easiest topic. I'm not sure when like DP will come. You shouldn't be like underconfident using greedy because greedy is really easy. See, basically cadence, don't worry about the cadence algorithm. The problem statement is you're given an array A, you have to find a subarray which has the maximum sum. You don't have to print that subarray, you just have to find the maximum sum. Now, many people wrote yes, right? Can you tell me how will you solve this problem? Unmute yourself and just
we'll keep adding the values from the index 0, and
Okay.
at each iteration we'll update the maximum value, and whenever the summation is less than 0, then we update the value to 0.
Okay. Now can you connect GP? Like can we connect this to greedy? How is this greedy?
It's greedy because whenever we found a negative sum, since we don't need a negative sum, we will greedily initialize the variable to the 0.
Yes, yes, yes. See, once like okay, let me first tell you.
अगर एक बार हम मैक्सिमम सम पा चुके हैं, अगर उससे नीचे जा रहा है तो हमको वो लेने का तो कोई मतलब नहीं होगा। इस वजह से हम ग्रेडली वो लेना नहीं चाहेंगे, तो हम आगे बढ़ते रहेंगे और वो छोड़ देंगे, इसलिए जीरो करते रहेंगे। इस वजह से ये ग्रेडली अप्रोच फॉलो कर सकता है।
Yes. So first of all, let me give all the people an idea. So basically at each, like you'll start from here and maintain a sum variable. You'll add these values. You'll keep adding these values to your sum. And at each point, let's say this is your answer, you'll take maximum of answer comma sum, which is like you'll keep updating your answer, checking that it should be maximum. And in case your sum turns out to be less than 0, you'll make your sum equals to 0. Now, how is this greedy? Let me tell you how is this greedy. See, first of all, forget about greedy. Why we are doing this? See, we are doing this because if sum turns out to be 0, this simply means from where I'm starting. If I make sum is equals to 0 at a point, I'll change my left window. You can consider these as like left bracket and right bracket. So currently where I am, it can be considered as a right bracket, and the last position where I had my sum as 0, it can be considered as a left bracket. So when I'm making my sum 0 at the current state, I'm shifting my left to that position. Why? Because there is no point in adding these to my further subarrays, because this value is negative. So this will only decrease my sum. So this is the basic general idea. But why is it greedy? See, once you do this, sum is equals to 0, you have already shifted your left range or left boundary to the current position. You will never shift this left boundary towards left direction. You're never going to shift this back. So that's why this is greedy. Now, I'm not going to give this much time. I'll directly jump on how we can connect this to the workflow. Is it okay?
Are we updating the sum at every step?
Okay, let me show you the code also. Like I actually have the code. So first of all, let's look at this pseudo code. So pseudo code is, first of all, we initialize, that is what is the maximum so far. So initially it is int minimum. This is our final answer. That is maximum so far. Then what is maximum ending here? So initially it is 0. This is basically the sum value. So now we loop for each element of the array, and maximum ending here is like we'll add this element to our maximum ending here. So now if maximum ending here, like maximum ending so far is less than maximum ending here, we'll update our maximum so far. This is now the bigger value. If maximum ending here turns out to be less than 0, then there is no point in you including those elements. Why? Because these elements are contributing a negative value. So we'll make our maximum ending here goes to 0. So now is it clear? Is it clear?
Yes, that's got it.
Okay. What about others? Just quickly write a yes, no in the chat. Okay, perfect. So now
one
yes.
doubt here. So this
Yes.
is maximum ending here is less than 0. We set it as 0. But
Yes.
the elements which are contributing, which are making maximum ending here lesser, can start before also. Then why does this work?
Okay, I quite
It's
didn't
like
get it.
whenever we are encountering a negative element, we have to change it. It's like that.
Like, what was your doubt? If the maximum ending is?
Ending here is less than 0, then they are setting it to 0. But
Yes.
because you said that the elements after that, they are contributing to a negative value. But I am saying that elements before that can also contribute, right?
Like, yes, you're saying that these elements, I'm making the like if at this point maximum ending here turns out to be negative, then I'm making it 0. So you're talking about what about at this place, right?
Yes, because these can also be negative elements. So
No. It's not possible that this was also at this point it was also negative, because if at this point if it was also negative, I would have made 0 here also.
no, I am telling the elements may be negative. The array element.
At the, in this place or this place?
In this place, like
The left.
it's reducing the value of maximum ending here. It's not making it negative.
Like I also I did give me an example.
Suppose maximum ending here at the first dash is 90, then
Okay,
there the element, suppose minus 15, in the next, then it will reduce it to 75.
Yes.
Right. We are not
Yes.
setting maximum ending here equal to 0 here.
Yes. Because if I start my, like, if I have my left boundary here and my right boundary here, so this value may be x. If I have my left boundary here, the sum will be x plus 75, right? The contribution of this part is 75. So this is positive. So I like to include that. If this was minus 75, then I won't include it. Is it okay?
Element is minus 15, right?
Yes, element is minus 15, but this complete part is contributing you plus 75.
Okay. So when the total contribution is negative, we make it.
Yes. Let me show you the pseudocode again. So here at this place, I'm making maximum ending here. I'm not checking the individual element AI. I'm checking if maximum ending here is less than 0. Is it okay?
I want to ask, we are taking minus 15 here because we are thinking of contiguous subarray, right?
Yes.
If it won't be contiguous,
then
we won't
it's a
be taking
completely
minus
different-
15.
yes. Okay, can someone tell me, if I don't have to find contiguous subarray, how will you get the maximum sum?
Just sort it.
Just ignore the negative ones.
Just take the positive elements there.
Just take the positive ones.
So it is not a DP problem and it is not a greedy problem. You just, like, it is kind of greedy only. I won't say like it satisfies in greedy. It is just an ad hoc problem. Like, just sort it and take the positive elements, because those positive elements will be giving you, all these elements will give you positive contribution.
If all will be negative, then first one, right?
If, like, then it depends on the problem statement, whether you have to whether you can output 0, whether you can select no element, or whether you have to select at least one element. In case you can select 0 element, you'll output 0. In case you have to select at least one element, then you'll output or select the minimum element, not the minimum element, the maximum element. Is it okay?
Sir, the
no.
sum of positive elements will be for a subsequence, but for a subarray, how can that be?
Sum of, okay,
So-
for like, okay, you're talking about the cadence algorithm. There's this problem.
You were saying, if you have to find a maximum sum, just take the positive sum. But I'm
Yes.
saying,
That is for, I was asking that for just when you are not given the constraint that the element should be a part of contiguous subarray.
Oh, okay.
Then you just select the positive elements. So let's go back to this. So this is the pseudocode and this is the actual implementation. So let me just zoom through it. So basically, this is like, if cadence algorithm is asked to you in an interview, they'll expect you to write the code. Okay. So this is the actual implementation. So initially it is int minimum and max ending here is 0. So you add this element to max ending here. If max so far is less than max ending here, you'll update your max so far. Then if max ending here is less than 0, you'll update your max ending here as 0. Finally, you can return your max so far. So I think this will be clear to everyone, right? I'll jump directly to that part. This is, just write a yes, no in the chat. How is this connected to cadence algorithm? Just write a yes, no in the chat quickly. Okay. Instead of writing yes, just write a no if there is something that you're missing at this point. Just write a no. Anyone? Yes.
I just want to know that this problem can also be solved using DP with the OFN. And the constants of the array are 10 raised to power 5.
How will you solve this using DP?
Pick not pick approach.
Pick
and non-pick approach.
Pick a not big approach. What is this?
Pick and not pick.
Like, just write it in the chat.
Take and not take.
I still don't get it.
He's saying pick and not pick. Like, if we
Okay,
are
okay,
at
okay,
an index,
okay.
either we
Okay,
are going
yes,
to
yes,
pick it
yes,
or
yes,
not.
yes. Okay, yes, I get it. Yes, it can be solved using DP also, right?
But how, after solving it DP, how we get to know that this problem can also be solved with greedy?
Okay, actually, the intended solution for this problem is not DP. You're talking about, like, I don't want to discuss that thing, but you're talking about this thing, right? DP, you have two states of n, right?
Yeah, fine.
Yeah, this is not actually, like, you'll learn this in DP. This is not actually applicable for everything in cadence algorithm. Like I said, this is the problem statement that I showed you. This is just the basic. You won't be asked exactly this thing. You'll be given a variation of this.
Okay.
And okay, try avoiding DP problems, DP question. Like, I know that you might be confused, but some people are already complaining in the chat that we are discussing DP more than greedy. So
No, my question is that I am able to solve this problem with DP, but how I am able to know that this problem can also be solved with greedy?
yeah, I'll come to that part. Like
First
basically,
at the first when I saw this problem, I am unable to click the intention of greedy of this solution of this problem. I want
So
to know
let's-
that thing.
so maybe when we are discussing DP, we'll have a better discussion at that point. Maybe some other mentor will be teaching you that, but I'm pretty sure that all these points will get cleared at that point. But should we just go with the basic flow right now?
Okay, fine.
Yes, okay. So there are initialization, then we have selection, then we have feasibility check, then we have update, and then we have termination, right? Like we repeat these steps. So this is termination. Now, first of all, what is the problem? We are given an array A. So we have an array and we have to find the maximum sum subarray. So maximum subarray. Okay, just give me a minute. Okay, and just give me. Okay, I'm really sorry for that. So basically, I was saying initialization. So what is initialization? Initialization in this case is that maximum sum here, or let's say just sum. Sum at this point is 0, and your answer is also having some value. That is, what is the maximum sum subarray value? Is maybe int min or something, right? Int min, or this can be 0 also. In case you are given that, you can select a subarray of size 0. In that case, you'll initialize your answer to be 0. Now, what is selection? Can anyone tell me what is the selection here?
Adding the values?
Yes. So this thing is basically in my sum, I'm going to add the values. Sum plus equals to A of I. Now, what is the feasibility check here?
Condition when it is less than 0.
Yes. No, not less than not less than 0. The feasibility check is whether this is my answer or not. So this is if answer is answer is equals to maximum of answer comma sum. This is the feasibility check, whether this can be my solution or not. Now, what is update here?
Checking it is less than 0.
Yes.
Sum become less than 0. Make it.
Yes, that is. So I'll update my sum is equals to 0 if this turns out to be less than 0. And then I'll repeat these steps and finally I'll get my answer. So is this thing clear to everyone?
What's the last part after
termination? No, after termination. This is just repeating steps 2 to 4. You'll repeat these steps for each of the, there are n elements, right? So you'll do this for all the n elements. Is it okay?
Okay.
Termination. Okay, so let's go back to this. So now we have discussed the problem. We know what are the different, what is the basic workflow for a problem, how we can use these things. So we have a general idea of this. So now let's look at another problem. This is jump game. Now I would like all of you people to contribute for this problem. Okay, so initially we are given an integer array nums and we are initially positioned. This is different than the problem that I initially asked you. Okay, so we are initially positioned at the array's first index, and each element in the array represents the maximum jump at that position. So we have to return true if we can reach last index, otherwise false. So how do you think we can solve this problem? And also tell me, what is the feasibility? How are you checking it is optimal? This is not a DP problem. Just think about it for 1 minute. I don't want to directly jump into the solution. So, okay, let me explain the problem.
You just told 5 to 10 minutes ago that this is a DP problem.
No. That was different. See, this is how you get confused. So the earlier problem was the array is same. The thing is same, that you'll jump from this place to this place, this place to this place. But in that problem, you had to return the minimum number of gems. Now you just have to tell me whether it's possible to reach this place or not. Did you get my point?
Yeah,
Yes. Yeah. So kindly note, this is a greedy problem, not a DP. Like if you're solving DP, finally, if like at that point, if you get some value for like minimum number of steps to reach this point, you can definitely tell, okay, that this point is reachable. So yeah, this can be solved using DP also, but the time complexity and space complexity will be much more. But if you're just required to find whether it's possible or not, then use greedy, right? If you try to use DP here, maybe you'll use n square approach. But the constraints for this problem will ask you to solve this problem in overfan. So this is a greedy problem. Now just think about it for a minute and tell me how this can be solved.
मतलब हम लोग को जो मतलब एक ये बना लेंगे वेक्टर ऑफ बुलियन वाला, सबको फॉल्स इनिशियलाइज करके, और हर पोजीशन से मैं जहां पे जा सकता हूं उसको ट्रू मार्क कर दूंगा, और मैं तभी जंप करूंगा जब क्या बोलते मेरा ith पोजीशन ट्रू मार्क है ऑलरेडी, और फिर लास्ट में चेक कर लूंगा कि मैं nth पोजीशन पे पहुंच पाया हूं कि नहीं.
Okay. So everyone gets the idea what he was trying to say, right?
Similarly, we can start from the last index and go backward.
Okay. Now I want someone to tell me why this will fail. Like first of all, everybody gets the idea. The idea is we'll make another Boolean array. Initially, say this is visited and everything is initially 0, and we'll start from this position. Like we'll start from this position and we'll jump. So initially this is just visited 1. So from this position we can jump here. So we'll mark this as 1. Then from this position maybe we can go here. We'll mark this 1. And finally, if this position is visited, we'll say that we can reach the last place. So can someone tell me why this will fail?
हर इंडेक्स पे जाके चेक करेंगे, मतलब जिस पे अभी गए हैं उस पे
I
नहीं.
want to ask, is this given that we
I
are
think the
going to
zero
start
है.
from the 0th index?
Yes, we are going to start from 0th index.
So
And
the
the-
answer will never be changed if we are given that we are going to start from 0th index.
Okay.
It will be given.
This is the maximum length that you can jump. You can jump from this place to this place also, right? Let me tell you why this solution will fail. This solution will fail for this test case.
We will make one up to the maximum length, not up at that point only.
Okay, I'll tell you that also. Just give me a minute. So for this, if you want to go from here to here, you won't directly jump to this place because from here you cannot go any further. So from this, you'll go to this place, and from this, you'll go to this place. Now, someone said that we'll check for each and every possibility. So if you'll check for each and every possibility, it is n square.
Can we just simply like iterate over the array? Like let's say if I'm at index 1
Yes.
at 2, so I'll just add 2 into my answer and take like I will take one jump to index 2, which also contains.
Perfect. I get the idea.
So
Yes,
I'll-
yes.
yeah.
Yes. I get the
And
idea.
I think I can use prefix sum over here.
Oh, no. Like the thing that this girl was telling is okay. Like I'm not sure that that was girl or not, but yeah, it is the perfect solution for this. See, when you're at this point, you can find what is the maximum index that you can reach, right? So you can reach each of these indices. And then if you're at this place, it is always possible, like now, since your maximum reachable place is more than the current place, you can reach this place. There's no like doubt in there. So from this place, just try to see whether if you include this jump, whether or not this max position that you can reach is farther from this place. Okay, let me show you what I'm telling. 2, 2, 0, 3. So initially you are here. From here you can reach this place. So maximum place that you can reach is index 2. This is index 0, 1, 2, and 3. Then you come to this place. You check the maximum place that you can reach is 2. It is farther than this. So you'll say, okay, I plus AR of I. So this is the maximum place that you can reach if you start your jump from here. So basically you can jump till here. So finally, you can check if the farthest place that you can reach is more than or equals to n, then it's true, otherwise it's not. So first of all, just tell me whether the solution is clear to you or not. Then I'll jump to that basic workflow and connect that to this. And then I'll also show you the implementation. Okay, no. Someone said no. Okay, no. Why this works? Okay.
No.
Hello.
Okay, yes.
So I have one idea that if I am at a particular index,
Yes.
so I can mark 1 by adding that value, and at that index I will mark 1, and after that I will add -1. And after that, if I just recompute it, means I just do prefix sum,
Okay.
can't it be solved?
Like how, if you're given 2, if you're given 5 and maybe a 10 and then some zeros, how you're going to solve this?
So now, first of all, if I have 5,
Yes.
so I'll go up to 5th index and I'll add
Yes.
1 over there.
Oh, so this is
Means
0,
I-
1, 2, 3, 4.
No,
Okay,
no,
somewhere
sorry,
here.
sorry. If the value is 5 over there, so I'll add +1 over there, and at the 6th index I'll add -1.
Okay.
So then after that, like this way, if I do for all the index and just
Like how will you get the answer for this?
so if I find 1 at the last index, then it should be
For this you are not going to find 1, right?
if I start for this 10, if I add +1 over there,
Yes.
and after 10th index, means from there adding
So
10.
okay, so this is also possible then. 5, you have some here, then you have 1 here, then there are many zeros, then there is a 10 and a 1. So you have a +1 here and a -1 here. So maybe you are saying that you can reach it, but you cannot reach this point itself.
Yes.
So you'll first have to make sure that you are able to reach this point. Then from this point, maybe, yeah, your solution works. If you are able to reach this point, then definitely you can reach this point. But what is the guarantee that you'll be able to reach this point, right? Okay, so let me explain the solution again. So the solution is, you're given this array. There are some jumps, like this is the values, x, y, z, alpha, beta, gamma, delta. So these are the indices. And you are starting from this place and you want to reach this place. So initially you are at this place, right? So from this place, I will say, what is the maximum index that can be reached? It is 0, that is this index, plus x. So in other words, this is I plus a of I. So this is the maximum index that can be reached from this point. If I start from this place, if I jump from this place, so if this value turns out to be more than this value that is currently for my, I'll update this value, right? So right now, maybe this is pointing to this thing. If this x was 3, so coming to this place, I'll check, okay, whether if the maximum index reached is more than or equals to I. So I can reach this ith place also, right? If this is I, if maximum index reached is more than equals to I, right? There's a way to reach this place also, right? If I can reach a place which is farther than this point, I can reach this place also, right?
Yes.
So for this place, again, I'll see what is I plus AI. If I plus AI is more than the maximum index reached till now, I'll update it. If at a point I see that I cannot reach this index itself, like I is more than maximum index reached, at that point only I can return false. I can say that it's not possible. So now is the solution clear? I'll connect it to workflow.
I am clear with the point, like when you are doing I plus AI.
Yes.
And you are checking if we can reach I plus AI. But the next
No, I'm not
point
checking
when
I
you
plus AI. I'm not checking you can reach I. I'm just saying that from this index, if first of all, I'm just checking for, like, currently if I'm at this index I, first of all, I'm going to check if max index reach is more than or equals to I. This simply means that it's possible to reach this index. If it's not possible to reach this index, I'll simply return false at this point itself. Return false.
Okay, I got
Otherwise,
it.
yeah, if I can reach this point, then I'll try to jump from this point. So if I started to jump from this point, I can jump to any place between this point and I plus AI. So if I plus AI is more than maximum index that can be reached, I'll update this. So I'm going to take a test case. I'm going to take
There is a
test case.
pseudocode, like before going to next I, we are going to check if we are able to go to that I by checking the maximum value we have currently.
Yes.
Okay, thank you.
So I'm going to take this test case. So what initially my maximum index that I can reach is 0 because I'm at that place, and then 3. So what is the place that I can reach from this? 0 plus 3. So is 0 plus 3. So first of all, tell me, this is my I. So I maximum index that can be reached is more than or equals to I, right? Yes, no?
Yes, getting.
Okay. So now that means I can jump to, I can be at this place. So now 0 plus 3. If 0 plus 3 is 0 plus 3 more than maximum index that can be reached? Yes, it is. So I update my maximum index that can be reached to 3. So it is pointing to this place now. So I'll come to this place. So now, is maximum index that can be reached more than this I index? Yes, it is. So I'll come to this pool. It means that I can come to this place. Now I'll check, is I plus A of I? This is 1 plus A of I, that is 2. So is 3 more than maximum index that can be reached? No, it is not. So I won't update it. Then I'll come to this place. Can this place be reached? How to check this? Is maximum index that can be reached more than or equals to I? Yes, it is. So I'll try to jump from here. So what is the maximum place that I can go from here? It is 1 plus, not like I plus A of I. So I is 2 plus A of I. 2 plus 1, it's 3. So the maximum place that I can go from this place is 3. So I'll see, is it more than the maximum index that can be reached? No. So I won't update this. Now I'll come to this place. Now is I more than or equals, is maximum index that can be reached more than or equals to I? Yes, it is. So I can come to this place. So now what is the farthest place that I can go from this place? So it is 0 plus 3. So this is 3. So should I update it? No, I shouldn't update it. So then I'll come to this place. So this is I, maximum index that I can be reached. It is 3. So is now maximum index that can be reached more than I? No, it is not. So I'll return false. Is this thing clear to everyone?
So it's a greedy solution.
Yes, this is a greedy solution. I'll connect the basic workflow with this.
Basically, this check is A plus AI greater than max, and
Yes.
the inclusion is just include checking for the next element and include
Yes,
that.
yes.
Right.
I am clear by the solution, but I just have a little doubt.
Yes.
What is the prospect of greedy here?
Yes, I'll connect that to that. Like, see, there are 5 parts: initialization, then there is
Selection,
then there is feasibility,
feasibility,
and then there is
update,
and then there is termination. Then there is termination. So basically repeating these steps again. So what is initialization here? Initialization is that my maximum index that can be reached initially is 0. Maximum index that can be reached is 0. What is selection here? If I select this, what is the place? What is the place that I can go to? I can go to I plus AI. Now, what is the feasibility check? Basically, you'll have to look at this like feasibility check is happening here by I, if I is less than or equals to maximum index. Then only you can include this, right? And then the update part is maximum index that can be reached is maximum of maximum index, comma, I plus AI. And then you keep repeating these. If the maximum index finally is more than or equals to n, you have got your answer, otherwise no. Is it clear?
Yes, absolutely clear.
So this should be crystal clear, because see, this is a very easy problem. And this is one of the problems in which you will have to use greedy. There is no, like in the previous problem.
This is the easy problem.
Yes. This is the easiest, one of the easiest problems. And
how, I just want to ask, how is this, if someone has not done this question and
yes,
it is
yeah,
encountering this,
like, yeah, this is, yeah, you won't get the intuition. Like there are some topics, like basically, if you have not done something, you won't be able to solve the easiest problem. So that's the basic rule, right? You try to cover as many topics as possible. Because see, if you're going for an interview, the interviewer might ask you something like anything. So if you have covered all the things, you'll be at least able to answer easy things, not maybe hard things. But if you have not done something and he asks you a basic problem, then you won't be able to answer it. So that's the case. If you haven't seen greedy at all before this, that's why I wanted to cover basics today. I could have jumped into directly a complex problem, then these things would have been missed, right? And this is, believe me, this problem will be 900 rated on Code Forces. Like it will be less than 1000 or equals to 1000.
Yeah. Most of the Code Forces problem involve this type of intuition that we don't click.
Yes. So I'll show you the implementation also. This was the problem, right? So this is the solution. See how small is the solution, right? So basically what we are doing, so can jump is basically an int nums. So can jump till is equals to 0, and for each of the indices, I'm just checking if you can jump till this place is more than or equals to I, then you'll update this thing. Can jump till is the maximum of can jump till I plus nums of I. Otherwise, you'll break this. Finally, you can check that if can jump is more than n minus 1. This is nums dot size is n. So is this thing clear to everyone? And I think like this problem, I have taken it from the Google OA. This was asked in Google online assessment. Like this problem was also in the slides of the tutor that had taken the class previously. So in that, it was written that this problem is from Google. So basically, the problems are not that hard that are asked, but you should be aware of all the topics. So there's a question right now, why equality with I? See, basically equality means that you can jump till this point also. You can jump further or basically till this point. So if you are able to reach this point itself, then you can jump from further from this point also, right? You get it? If can jump till is less than I, then that means there is no possibility to reach the ith point itself. So then you can just break. There's no point checking further. So is this problem clear to everyone?
Yeah.
Okay. Now we are going to see. First we did cadence. I'm assuming like cadence was the easiest problem. Like cadence was, you all were aware, so you had an intuition how to do cadence. Then we came to this problem. So like some people had the intuition, some people had it out, but right now I'm guessing that this is clear to everyone. So now we're going to go to another problem, and that problem we'll see there's a definite pattern in greedy problems always. And I want to cover in the fundamental class, I just wanted to cover, like I just wanted you to know that this type of things are also possible. So I'm going to go into one more variation of DP, like of greedy problems. Okay, so this is the problem. So we have to find the original array from the doubled array. So an integer array originally is like there was an original integer array and it is transformed into a doubled array. So what is a doubled array? Each of the elements in the array are multiplied by 2 and are appended in the original array, and then the array is shuffled. The elements, all the elements in the array are shuffled, and you have to tell me, or you have to return the original array. So let me write the problem statement here. Like there are elements alpha, beta, gamma. Let's say alpha, beta, gamma, and delta. These were the elements of the original array. Then the doubled array is nothing but, first of all, you keep these elements, then you add twice of these elements, and then this thing, and then you shuffle these elements, and this array is given to you, and you have to get back this array. So can you tell me how will you solve this problem? Any idea? Any random thing? So one thing
just
I have got
sort it
is,
and just
okay,
first of all sort it and make everything a true or a map, or we can just use a set and then we can iterate and check if we are on beta, if their beta by 2 present, if we are on gamma, is their gamma by 2 present, and when we will be on 2 alpha, we will be dividing it by 2 and we will be finding like there is alpha present, so one of the element is alpha, then we go and we can delete alpha from that and then 2 beta, and we can continue like this.
I get the idea. So is everyone, like, did everyone get the idea what he was speaking? Achha, what is alpha, beta, gamma? Alpha, beta, gamma is just random elements. Assume this is 2, this is 10, this is 1, this is 3. So this is 4, 20, 2, and 6.
Sir, in this question, do we need to return the order of original elements?
No, you cannot have the you cannot have the order. Like, how can you get the original order?
Exactly.
There's no way to get, because the elements are shuffled, right? So even though like you cannot get the original order. Yep. So basically you should return 2, 10, 1, and 3 in any order. If you're given this array.
I think that approach I told will be wrong.
What?
I think the approach I just told can be wrong.
Yes, like I'll come
because if 2, 4, 8, 16 are present and their doubles are present, how will I going to find out?
सबसे बड़ा से चालू करेंगे, मतलब जैसे 2, मतलब जो सबसे जैसे 20 है तो 20 जो भी नंबर्स आया होगा वो मतलब उससे छोटा ही होगा, बाय 2 करके देखेंगे ऐसे करके.
Yes. See, the earlier guy told 50% of the approach. He was correct. He was not wrong. But how do we implement it? How we pick the solution greedily? So the second guy told us we pick the biggest element first. So if we are taking the biggest element, then it's 100% sure that this element is a multiple of something that was available in our original array. right? It is a multiple of these things. If I've sorted these values, like let's say these are the sorted values, then it is for 100% sure that this value is a multiple of any of these. Do you get it? It's not possible that there is a multiple of this also. Why? Because this is the biggest value, right? So I know this is confusing right now. Now let me tell you. Now let me see how I solve this problem. See, instead of going from biggest to smallest, we can go from smallest to biggest also. So let's take this case only. If I have 2, 10, 1, 3. So I have 2, 10, 1, 3. My doubled array will be 2, 10, 1, 3, 4, 20, 2, 6. Then I reshuffle this. So after reshuffling, I get maybe 1, 2, 2, 3, 4, 6, 10, and 20. Right. So what I'll do, I'll store each of these elements in a multi-set. And now see, the solution is clear to us. We have to pick an element and we have to see if the double of it is in the array or not. If there is, we'll remove both of these elements. But how do we pick that element who we are 100% sure that is one of the original elements? So we'll pick the smallest element, because see, if there are some elements in this, like this 1, 3, 2, and 10 that were a part of original array and others are not. See, how we pick those elements only. See, if we are picking an original element, then if you're picking the smallest original element, there cannot be any element which is smaller than that, because the elements that we added in our array are double of these elements, right? So in my multiset, I'll insert all of these elements. Then I'm going to pick the smallest element from my multiset. Okay, and I'm going to push this answer in my, like push this value, smallest value, in my answer. And from my multiset, I'll remove two values. Let's say this value, like the smallest value is x. So I'll remove x and 2x. I'll keep continuing this while my multiset has size. Finally, I can print my answer. So is the solution clear to everyone?
So at each point, we'll find the double of it and we'll remove the double part.
Double part also, and the single, like this value also, x also, if x was the smallest. So what is greedy here? What is greedy here? The greedy thing
element is guaranteed to be the smallest.
Yes. At that point, I'm deciding the fate that this is my answer. This is always included in my answer. And what is greedy? I'm just taking the minimum element always. Okay, if somebody's internet goes, like, was not, like, was buffering. So I'll repeat this. So let's suppose that this is the original array. This is the doubled array. Each element of the array is appended to the original array by multiplying it with 2, and then the elements of the array are shuffled. So what I'll do, I'll insert all the elements of my doubled array in my multiset. I'll pick the smallest element. Why smallest? Because it's guaranteed that the smallest element will always be a part of the original array. Why? Because the elements that I added were double of the original array elements, right? So that's why I'll pick the smallest element, I'll add it to my answer, and I'll remove two elements from my multiset. This x element, that is the smallest element, and 2 times the smallest element. Now again, I'll pick the smallest element again, because that element will also be in my original array. Is it okay now?
What if we are asked to print -1 if the answer does not exist for
Like
any given array?
majority of these problems, the solution always exists. Like, and in case the solution isn't exist, you can simply print -1 or anything, right? You can check if 2x is not, like, that's like, why will someone ask you that kind of problem? But you can check, right? If you have like, if the 2x doesn't exist in your solution. Okay.
When we remove 2x, doesn't both the occurrence of 2x will go away?
Yes, 2x will be 2x. This thing will get removed.
Oh, I mean, when we get 1, we remove 2. Will not both the 2 will be removed?
No. Like in multiset, there's an option to remove all the occurrences and only one occurrence, right? If you
Hi,
use,
Ankit.
yes.
What if we have negative number in the array and doubling it make it more smaller?
Yeah, for this problem, the constraints were given that the elements are more than or equals to 0, more than 0.
Okay, fine.
Like it is a different problem if there are negative elements also. You'll have to divide. Can anyone tell me how to solve that problem if there are negative elements also in the array?
Divide it into positive and negative arrays.
Yes, exactly.
Divide it positive and negative.
Yes, make positive and negative array, two arrays, and solve these two differently using two multisets. Is it okay?
Okay, fine.
And someone asked me that if I do map dot like not map multiset dot erase something like 2x, won't this get erase? Won't this erase all the occurrences of 2x? Yes, it will. So I won't use this. I will use this thing multiset dot erase multiset dot find. So what this does, this finds one occurrence of 2x and deletes only that. This gives you a pointer to exactly one value.
I just want to ask,
Yes.
it won't increase our time limit because every time we are going to check if the half of that element is present.
So yeah,
So
the time
n
complexity is going to be n log n.
n log n.
Yes.
Okay.
But why? Because checking if there is a half element, you'll use multiset dot find. Like anyway, for this problem, you don't have to check. You can directly erase it because the problem simply tells you that originally there was an array, and from that array they made a double array, right? So if there was an original array, then it's possible to get from the double array up to that original array, right? So if this is okay, I'll first show you the code. Yes,
Sir, in this problem, it is comparatively told that all the elements have their doubles present, like 2,
yes,
10,
yes,
1,
yes.
3.
Yes.
Okay.
Okay, so if this is clear, I'll show you the implementation quickly, and then we'll try to connect the basic workflow also for this problem.
Bhaiya, the greedy intuition in this question is that we are not sure about any particular element in between the array if it was present in the original or not, but the smallest one will definitely be in the array.
Yes.
So we just start building our solution from that point, right?
Yes.
Okay, thank you, Bhaiya.
Okay,
Hi,
so
Ankit, in multiset, average, best, and worst case time complexity is log of n, yeah, something of
log in.
Okay, fine.
So let's jump to the implementation. So this is the solution. In this, I'm first taking a multiset, then inserting everything in my multiset. Then I have my answer vector, and while my multiset has a size, I'm picking the lowest element that is in my multiset. I'm putting in my answer. Then I'm erasing the value from my multiset, and I'm erasing the double of that lowest value also from my multiset. So then I can either return that answer vector, or I can print it. So is this thing clear to everyone? Is this thing clear to everyone? Yes, no? Just write a quick yes, no in the chat. See, these are the three variations. See, if you now probably your thinking for greedy solutions have increased a little. Like I know the first problem was like majority of the people were aware of the first problem. Second problem gave you a little bit more idea, and that's why I think that reasoning helped you a lot while you were solving this third problem, right? If I would have directly given you this problem, you would have like faced a little difficulty. But once your thinking increases, once you have already earlier thought in that direction, it becomes more easier to get to the solution, right? So you see the solution for all the three problems that I showed you, the solution was very small. There is just a reasoning like this will work, this will 100% work. You should have that intuition. And from that, you try to make your solution brick by brick, like layer by layer, you get your solution. So in this, like let's quickly discuss what is the initialization, feasibility check, and termination update. So what do you think, what is initialization here? In this problem, okay, my screen share, did my screen share stopped?
Yes.
Okay, I don't know what is happening today. Okay, what do you think is initialization today? Like initialization here in this problem. Initialization is basically the thing that you do before you start your greedy implementation. Adding
answer array.
Yes, adding everything to the multiset is your initialization. So this is different. Initially, we were just initializing one variable. So that's why this is. Don't always think that initialization is something that you'll do for one variable or maybe that is fixed. No, initialization is something that will help you further during your implementation. Now, what is selection? This basically this
minimum element.
Yes.
Minimum element.
Yes. That is selection. Now, what do you think is feasibility check here?
Finding the double value.
Yes. Actually, in this problem, it's guaranteed that 2x will always be there. But if 2x was not there, then you would have to put an if condition here, right?
Yes.
That is feasibility check, not size, not anything. That is the feasibility check. If at that point, see, for this problem, the solution is guaranteed to be exist, but sometimes the solution might not exist and you'll have to print -1, right? So here you'll have to check that the 2x is in your multiset. If it is not in your multiset, then your answer is -1. So that is feasibility check. Now tell me what is update?
Erasing part.
Pushing into answer. Pushing
Erasing
into
is
answer.
Yes. You can consider all of these as update.
So
Okay, selection and feasibility. See, selection is
Mhm.
basically this thing. You're picking the lowest element. So this is the selection. Now, feasibility check in this problem, the solution is guaranteed to exist. So that's why I'm not doing a feasibility check, because what is feasibility check? It's telling you whether the solution exists or not if you are picking this thing, right? But in this, the solution always exists. So that's why I'm not having a feasibility check. Here, you would have to check if the solution is not always, like if the solution doesn't always exist, you'll have to check if 2x is in your multiset or not. That is feasibility check. Is it okay? Okay.
Basically, the same problem was there, but if it was modified to say that return only those elements in which it was doubled, then we would have the
Yeah, that is also, yes, that also qualifies for feasibility check. Then also you would have to see that 2x exists or not. So we are done with these. Now coming back to some, I think, yeah, we'll have to cover some more theory. Just bear with me because this is important, right? This is just some theory, and now we won't be discussing more problems. So there is just theory part left. So, but basically, what are the advantages of? Okay, what is pushback step? Pushback step can also be considered as your update. It's a part of update. Is it okay? You're basically updating your answer, right? These three. Okay. So now, what are the advantages of greedy algorithms? Greedy algorithms are relatively easy to implement. Like I showed you, all the three codes were really easy to implement. I'm not saying that they are small always. Sometimes greedy algorithms like tend to be very big because there are many conditions that you have to check. They can be more than one feasibility checks. DP solutions, on the other hand, they turn out to be smaller to implement. Like the code size is less, but they're hard to implement. You should have more mathematical reasoning behind it. Now, the second advantage of greedy algorithms is they work for problems where making the locally optimal choice at each step leads to a global optimal solution. So basically, this is the thing: when you are like locally choosing an optimal solution, it should lead to a globally optimal solution. If it is not leading to this, greedy solution won't work. Then the third point is they can provide quick solution on large scale problems when other methods might be computationally expensive, like deep or maybe brute force. So there is nothing to like. I don't think anyone is having any doubt in this part, right? Okay, so let's go ahead. So what are the limitations of greedy? See, greedy algorithms might not always produce the best solution as they lack global awareness. So if you are trying to pick a locally optimal solution, you don't have any idea what is like in front of your current index, what happened before. We're just trying to pick a locally optimal solution. So that's why you don't have in mind, you don't have the global awareness in mind. You are not aware like if there is a negative element, positive element ahead of you, or it is behind you. You completely lack that awareness, right? So that's why in those cases, greedy algorithms might give you wrong answer, or maybe not the most optimal solution. There's also a risk of getting stuck in suboptimal solution, especially if the local optimal choices accumulate. So what does this mean? See, you will cover this much more, these choices and suboptimal choices in DP. So basically, at each point we are making a choice, right? So if these locally optimal choices keep accumulating, like whether to select this or not to select this, if these choices, wrong choices, keep getting selected, or the final thing that you'll end up with will be very far from the optimal solution, right? And this can happen because you are only looking at the locally optimal solution. Then we need to careful analysis is required to ensure the greedy algorithms indeed lead to an optimal or acceptable solution. Now, how do we take care of this? Like all the three problems that I showed you, we had the feasibility check. We know that, okay, if we are doing something, it will always lead to, you should have that thing 100, like you should make 100% sure that the thing that you are selecting right now or you're not selecting will always lead to the optimal solution. So then only greedy solutions work. So today, this was just the introduction. In the next class, let me tell you what will happen in the next class. I won't cover any basic thing. I'll show you some of the like proofs but I don't think proof is much of that help. Like majority of the times, greedy problems like these problems, do you actually required like needed some kind of written proof for the three problems that I showed you? Just write yes, no in the chat. Do you think like okay? Just tell me if in a problem, if in a contest you get these problems, will you try to prove this using pen and paper, or will you just prove it in your head that okay, this works? So that's why proving greedy solution is important. But when the problem really requires you, like when you're not completely 100% sure, but for majority of the problems, it's just a waste of time if you are start proving everything from scratch. But in the next class, I'll try to take those proofs also if I get time. But in the next class, I'll pick up like we'll go through advanced topics. Make sure that you brush up. Like I'll give you some problems also, daily practice problems also. So make sure that you do those problems in the first part of the half week. I'll give you relatively easier problems that are covered in this class, and then in the next class, like after next class, I'll give you hard problems.
So I was just saying, if you are going to provide us easy problem, then can you increase the quantity of problems? Because if
Yes,
these
right.
are greedy
I want
problems,
easy problems. So right now, like you're talking about the last class, right? I gave easier problems last time. Was this okay? I didn't take class for this level, but yeah, I get it. If like tell me just give in the chat that whether you want easier problems or a little hard problems, you will have much more doubt. Okay, see what will I do? I'll give you 30% easy problem and 70% hard problems. How does this work for everyone? And also give me a range. Like hard is different for everyone, right? What is the range? Like, don't give me a particular number. Just give me a range. What is hard for you?
1400, 1300,
Yeah, 13
1400
to
is
15
Somebody
something.
said 1900. See, 1900 greedy
No,
problems.
1900 is too far.
Yes, for 1900 you'll have to write a proof.
Yes, about 1400.
And for 1900 you'll have to use multi-set pairs and those things. Greedy solution do exist. Like, let me give you an example. Are you aware of graph algorithms like Kruskal's and Prim's?
Yeah.
Yeah.
Yeah, little bit,
What
but
do they give
not
us?
remember that much.
Anyone? What do they give us?
Minimum path.
Minimum spanning tree.
Yes, that is a greedy algorithm. Both of those are greedy algorithm. So I think you are not aware of that, but both of those are greedy algorithms. So at that point, those kinds of solution you'll have to write. So that's why I'm not willing to go to directly jump to 1900 at this point. Maybe after, like, I'll give you definitely, like after Wednesday, I'll try to give you some of those 1500 also. But I don't think that is required right now.
Yeah, you can just provide, if you are going to provide 10 problems, you just can provide 3 to 4 problems up to 1000, and
Yes,
after
and
6
then
problems up to
1400.
1400.
Yes, yeah, that is what I was thinking. And apart from this, like I said in the I would really suggest that you come prepared. Like you shouldn't have any doubts regarding today's class. Like I think covered everything in today's class. There is nothing left. And
How many classes will you take on greedy?
classes. The second class is going to be like I could have done like I could have really skipped this class. Like I could have just gone like not gone in depth, and I could have just told you, given you those two problems and not solved it, and then I could have gone in advanced stuff. But I think this class helped, right? Can you just write yes no in the chat if you think that this class helped? Okay. Yeah, I would see greedy is one of the topics you should have. See, majority of the people get confused when to use greedy and when to use DP. Those are actually not different pictures. But yeah, right now since this was the first class, there was no actual need of DP. See, RAM and
both we use together.
Yes.
Both we use together.
Yes. Sometimes. Yes, you should have idea of both. Then only you'll be able to write a perfect solution. So that's why I took some liberty and discussed why. Like, see, if you have a doubt, why to use greedy here when you have a solution of DP in mind? So then there is no point in teaching or like studying greedy, right? You should know. First of all, you should know that why shouldn't you use DP either because of the constraints or when you should only use DP. Like those, I think that jump problem. The first problem can be solved only using DP, and the second problem that we actually solved today, that was a greedy. If you solve that using DP, your time complexity will be much more than the greedy solution. So that clarity will only come when we have discussed both. So I think that's it for today, and I have already shared the feedback form. Kindly fill that. Okay.
Sir,
Hello.
Yes.
Sir, I have one request from you. Like from next time, while you are explaining your approach, please don't inculcate other students' approach because we actually want to follow your path on greedy. We don't
Yes,
want the solution of that.
Yeah, that might be disturbing if I started answering some other people's stuff. But I get so many problems. Like I think that if I just wait for 10 minutes, the chat section will be filled up and I won't be able to identify where I left. But yeah, from next time I'll make sure that once I've done with my explanation,
Actually, I have the same problem. Like people start speaking in between. You can complete and then take the questions, right?
yeah, okay, sure. Right now, I think the batch size is also really big. So that is also one of the problems. But anyway, from next time, I'll make sure that I'll try to take all of these things into consideration. Okay.
And sir, also the problem you have discussed, can you please provide the link of those problems?
Like I think these are already provided in the chat. I'll share the slides definitely. Those are already provided. Like I'll share the slides with you. If you just copy paste the problem, I haven't changed the problems. If you just copy paste those problems, you'll find the link to those problems on NeetCode. Okay.
Okay.
And those are also given in the chat. I haven't changed the problem. Like the problem statement.
भैया मुझे एक क्वेश्चन है एक्चुअली मुझे ना थोड़ा जल्दी एक बार में समझ में नहीं आता है बार बार देखना पड़ता है तो जैसे बहुत सारे डाउट्स आ जाते हैं बीच में बहुत सारे क्वेश्चंस तो अभी भी मुझे आई थिंक देखना पड़ेगा फिर से तो इसका कुछ सोल्यूशन है क्या कि मतलब एक बार में चीजें नहीं आती बहुत सारे क्वेश्चंस आ जाते हैं माइंड में
Yes, it happens. See, there is no like guilt in suffering because see, even if you're suffering after 1 month or maybe after some around down the line 10 weeks, you'll be better. So you don't have to be ashamed. Like if you are asking doubts and other people are saying that okay, you should like even like see, I understand other people's also. See, that's a valid point. I shouldn't answer each and every random doubt between my explanation. That is 100% valid point. There is no excuse around that. But what I can do, see, from next class onwards, I'll try to give a time after the class and I'll try to answer as many questions or doubts after the class. So that's work for everyone because I won't waste everyone's time, right?
हाँ ऐसा भी होता है बहुत सारे क्वेश्चंस आ
Yes,
जाते हैं तो और
and one
कंफ्यूज
thing,
हो
like if you have doubt, just raise a query in 10 minutes. We'll meet we'll meet and we'll discuss. I won't give you, like, I won't try to resolve your doubt on the chat. We'll meet. Just try to like go through this recording. The recording will be provided to you very soon. Just try to go through the recording once and do solve the problems. Even if like you're not able to, just give it a try. Okay.
Bhaiya, is it the right time to ask a question about the topic?
Which topic?
The greedy one that we just covered.
Okay, you have a doubt right now about regarding what? Regarding the class or it is a separate?
Yeah, the class, obviously.
Yes. Ask me.
Okay, so I think of greedy in this way, like suppose we have computed some solutions so far and we are at suppose in middle of the arena and now we're deciding how to proceed forward. So we usually like have pre-computed something and we look at that to decide on like usually like the previous element or something, just like the before element, उसके basis पे हम देखते हैं कि like आगे कैसे बढ़ना है. And greedy में हम we don't have to worry about multiple
in greedy
solutions.
we make sure that either if this is included, then it will be included. Otherwise, if you're not selecting it, it won't be included. We won't revisit our choice. In DP, we revisit our choices.
Yeah, exactly. Like multiple choices, we have to worry about like what was the solution in last 1, 2, 3, 4 steps ago. But in greedy, like just before, we don't have to worry about earlier.
Yes.
But when we try to solve DP solutions, we store our answers in a way where we don't have to go back to all of those, but the previous answer contains all of those solutions and we just can look at that. In that way, DP and greedy are similar, but DP is storing multiple answers, multiple optimal answers, and we can just pick the best optimal. But greedy
for each choice, basically.
Yeah, for multiple previous choices. Is that the right way to think about it?
Yes. Like this is the perfect way to think about this, and you'll get a much better clarity when the other mentors, like there will be a class on DP, right, very soon. So, but yeah, your intuition is 100% correct that in DP there is optimal, like we are storing optimal solution for each and every choice.
And yeah, just at any point, we can just look at the previous index and find the okay. Thanks, Bia. I just wanted to clarify because I'm trying to equate DP and gradient. You will like alag alag hai wo, don't compare them. But thank you for clarifying that they're pretty much in that regard similar. Thank you, Bia.
Bhaiya, what about Ravenkarp and
Yeah, I
KMP?
think I'll have to ask the manager. I think that is covered in strings.
But there was only a single class in string hashing, and Ravenkarp and KMP were not covered.
Okay, I'll see. Like, I'm not sure that I was following the curriculum that the last previous mentor gave me, so I don't think in that it is mentioned, but I'll see.
Yeah, in TLE website, it is given in level 4, Ravenkarp and KMP.
Okay, yeah, this can be one of the reasons that Ravenkarp and those things are covered in level 4. So
Okay,
anyway, I think the time is almost up. So I'll see you on Wednesday, and thanks for joining. Bye bye.
No, sir.
Okay, in case you guys like in between you